Okay. Hello, everyone. Welcome to our homework session. So just a quick announcement. The tutor that's doing the first question has some emergency today, and we will be uploading the recording of that question after the session. So today we'll start with question 2, and we'll cover question 3 and 4 after question 2. Okay. So now, Xiao, you can take away. Thank you.
All right. I'm gonna start sharing my screen for question 2. All right, so for question 2, we have a carbon-14. It's an important isotope for the dating or organic samples by using a first-order decay of its radioactivity. And we know that the original concentration of the carbon-14 is 20 units per gram, and now it is 4 units per gram, and the half-life is 5,200 years. So since it's first-order reaction, we know the integrated rate law for the first-order reaction would be concentration of the reactant is equal to the original concentration times e to the power of negative kT. And we also know that the K, the rate constant K, is equal to log 2 over the half-life. And since we know that the half-life is 5,200 years, so we know that the rate constant would be log 2 over 5,200. And that's going to give us 0.00014 per year as our rate constant. And now, since we already have the original concentration and the rate constant, if we plug everything in, as in so 4 equals to 20 times e to the power of t times rate constant. And if you solve for t, you'll get the age of the sample. And that's for question 2a. Are there any questions? Okay. For 2b, we have the Arrhenius plot. And this is derived from the original Arrhenius equation, which is written here. And if you rearrange it and you pull the 1 over t out as the x and pull the log k out as the y, you'll get a linear relationship between log k and 1 over t. So the first part of 2b, it's asking us for the activation energy and the pre-exponential factor A for reaction. And they gave us 2 data points. So to calculate the activation energy, we just need to know the slope. And you can calculate the slope from these 2 data points, which is plus 1.003 divided by 0.00333, subtract minus 0.003. Oops. And that's going to give you negative 1,000. And that's equal to our slope, which is negative E activation energy over a gas constant. And if you times the gas constant, which is about 8.31 something into it, you'll see that it's 8.31 kilojoules per mole is our E activation energy. And the same thing for the pre-exponential factor. You just need to plug in these 2 data points. Now that we know everything, we know the we know the gas constant, and the E activation energy, the temperature, and then the K. You can just plug in the data points, and that's going to give you the A pre-exponential factor. And the unit for the pre-exponential factor should be the same as the rate constant, which is 1/2. And that's for 2B. Are there any questions? Okay, I'm gonna go to 2C right now. So we have an enzyme that accelerates the rate constant to 10 times over the uncatalyzed reaction by perturbing the activation energy. Calculate the difference in the activation energy at 300 K. First, let's calculate the rate constant for the uncatalyzed reaction at 300 K. So we can just plug in the data points into the first order reaction integrated rate law. We'll see that K uncatalyzed is equal to actually that's gonna need us to know the pre-exponential factor and from the previous question, and I'll just tell you guys the answer that it's gonna be 7.4. So if you get the 7.4 as the pre-exponential factor, then you times e to the power of -8310 divided by 8.31 times 300. That's going to give you the K uncatalyzed, and that's equal to 0.264 per second. And then we know the K accelerated version is 10 times of that. So that's going to give us the K prime is 2.64 per second. And now we have the rate constant. We can just plug in into the Arrhenius reaction. 2.64 equals 7.4 times E to the negative EA over RT. And now you can solve for the activation energy, the new activation energy that has an enzyme present. And then you can solve for the difference in the activation energy at this specific temperature. And then for question D, you'll see that the new EA is going to be less than the previous activation energy. And how does this change the spontaneity of the reaction? And it's probably not going to change it because the activation energy is related to kinetics, and an enzyme does not change whether a reaction is spontaneous or not. And that's pretty much it for question 2. Are there any questions? All right, if not, I will stop my share now and feel free to send in more questions in the chat.
All right, cool. I will get started on question 3. So let me share my screen. All right, can everyone see my screen? Oops. All right, cool. So question 3 is about steady state. So we can start with part A, which is basically asking what steady state means and whether or not it's the same as equilibrium. So by definition, we know steady state just means that the change of molecules over time is zero. So the number of molecules in a given situation is constant. And this is, like we learned in class and in the last section, it's not the same as equilibrium, and where equilibrium is what all the concentrations decay to after time. So SS does not equal equilibrium. Okay, cool. Part 2 is asking us, under steady state conditions, derive the equation for the relationship between the average number of RNA and DNA molecules. So we know that the number of RNA molecules over time is 0, and we also know this equals to the number of DNA molecules times the rate of conversion, okay, R, minus the number of RNA molecules that are decayed, so times K negative R. And if we rearrange this, we get something that looks like R, K negative R equals ND K R. And then we can rearrange a little bit more to get NR is equal to ND K R over K negative R. And these are all averages, so we can write them as their average terms. Cool. Right, so that's for part 2. We're done with this one. We're done with this one. Suppose that the rate constant for RNA production is 100 per second. We want to calculate the expected mean value of RNA molecules per cell. So basically, in this situation, we're looking for the ratio of RNA to DNA, which is KR over K negative R. Looking for the ratio of the averages under a fixed DNA condition. So we just plug in our numbers here, 110 equal to 100 over 10 gives us 10 RNA molecules, or mRNA. All right. Cool. Sorry, one sec. As discussed in class, under steady state conditions, the probability that this cell has a certain number of RNA molecules generated is given by the Poisson. Use the rate constants given in part A. Using the rate constants given in part A show that more than 80% of the cells in this population will have a different number of RNA molecules than the mean. So for this, it's essentially just plugging in numbers into the Poisson. So not really going to walk you through the calculations, but we already solved for this value right here and this value right here, and we know what NR is. So just plug it in, and then you'll get a value that is less than 20%, which is what you're looking for, and that should be that. Cool. Yeah, that's it for question 3. We can move on to question 4, and I'm in chat if anyone has any questions.
All right, I'll be doing question 4. Okay, so question 4 kind of follows question 3, except it's giving you a different situation where, so basically a cell's survival will depend on the number of RNA molecules it has. And if a cell has greater than 20 or greater RNA molecules, it'll survive an antibiotic. And if it has anything less than that, it'll die. So basically, we just want the probability that the cell will survive, and specifically, we want the amount of cells that will survive in a population of 10,000. So based on this probability distribution, we want to first start out with calculating the probability that a given cell survives, which would be the probability that a cell has 20 RNA molecules. So as gone over in question 3, we can use the number of RNA molecules under steady state will follow a Poisson distribution. And we can use the following equation. And so we want to we want to find the probability of 20 RNA molecules, so we can just plug in the 20 to the equation. And next, so now we only need one more term to compute this probability, and it is that forward rate of RNA formation over RNA degradation, which, seen in the last question, was reflected by the mean. And we can identify this using the given probability distribution as the value of the number of RNA molecules with the highest probability. So see here, and so yeah, so assuming the cell has one DNA molecule, the average RNA molecules will be the KR over the degradation term, which would be 10 RNA molecules. So you can plug that in, and you can plug those values into the equation and get that probability. Another thing to note is, since you're working with really large numbers to the power of 20, we can get a better accuracy with taking the natural logs of both sides, or taking the natural log first. But you could also do it this way and just plug the numbers straight right in and get about the same thing. So, but in this case, like if you wanted to take the natural log of both sides to get a more accurate answer, you could just do the following, and then take the log of both sides, separate the terms by addition since they're all being multiplied, and then simplify them via logarithmic properties. And yeah, so once you'd get the natural log, then you could just exponentiate it and you'd get the probability. But yeah, you could also just use this equation as well. And then, okay, so now that we have the probability that a given cell will survive, which is the same as the probability that it has 20 RNA molecules, all we have to do is multiply the given initial cells times this probability, and we'll get the number of surviving cells. And that's the end of the question. Does anyone have any questions? All right, well, yeah, feel free to message me as well.
Okay, do we have any questions for question 2 to 4?
Would you be able to just go over the last part of question 2 again?
So Shihab, could you do the last part of question 2 again, please? Okay, I think he may be busy at the moment. We finished quite fast. I think he probably didn't expect a question at this time.